Have you ever looked at a physics diagram and just thought, wow, where do I even start? Well, today we're going to take a problem that looks pretty complicated, forces pulling in all sorts of directions, and we're going to break it down into something that's actually really simple. Let's jump right in.
So, here's our challenge. It all centers on this one single hook. But it's not just being pulled in one direction. Oh no, it's being pulled by three different forces, all at their own unique angles. Our mission, should we choose to accept it, is to figure out what's the overall effect. What's the one single pull that this hook is actually feeling? And here's the setup. You can see we've got a 60-pound force, a 40-pound force, and a 50-pound force. And yeah, at first glance, it looks like a bit of a mess, right? I mean, how on earth do you add up forces that are all pulling in different directions? It seems kind of tricky, but trust me, there is a super elegant and surprisingly simple way to solve this whole thing. Okay, here it is. This is the secret weapon for this entire problem. Instead of trying to wrestle with these diagonal forces directly, we're going to do something much smarter. We're going to break each one of them down into two simpler parts. This one idea is going to unlock the whole puzzle for us.
And these parts have a name. They're called components. Just think of it like this. Any diagonal pull is really just a combination of a side-to-side pull and an up-and-down pull happening at the exact same time. Once we separate them, we can just add up all the horizontal bits together and then add up all the vertical bits together, and suddenly the math gets way easier.
So every single one of our forces has a horizontal piece, we'll call that the x component, and a vertical piece, the y component. And the best part? To find them, we just need a tiny bit of basic trigonometry. Don't worry, it's not scary. We're just going to use cosine to find the horizontal part and sine for the vertical part. That's it. No crazy formulas, just two simple tools.
All right, enough theory, let's get our hands dirty. We're going to take each of our three forces and just methodically break them down into their x and y components. We'll just go one by one to keep everything nice and clean.
First up to bat, the 60-pound force. You can see it's pulling up and to the right at a 25-degree angle. So let's just isolate this one for a second and figure out exactly how much of its effort is going side to side and how much is going up and down.
And here they are, the only two formulas we're going to need for this whole section. To get the horizontal force, Fx, we just multiply the main force by the cosine of the angle. For the vertical force, Fy, we multiply it by the sine of the angle. All right, let's plug in our numbers and see what we get.
Okay, so for our 60-pound force, the math tells us it has a horizontal pull of 54.38 pounds and a vertical pull of 25.36 pounds. And see how they're both positive? That's just the math confirming what we can see in the picture. It's pulling to the right and it's pulling up. Perfect. One down, two to go. Let's move on to our next one, the 40-pounder. Now pay close attention to the direction here. It's pulling at 60 degrees, but it's below the horizontal line. In the world of trigonometry, we show that by using a negative angle, so negative 60 degrees. And that little detail, it's going to be key. We use the exact same formulas. The horizontal part gives us a positive 20 pounds, which makes sense. It's still pulling to the right. But check this out. The vertical part comes out to negative 34.64 pounds. And that's exactly what we want to see. That negative sign is the math's way of telling us, hey, this force is pulling downwards. And now for the last piece of our puzzle, the 50-pound force. This guy's hanging out down in the third quadrant, which means it's pulling both to the left and down. Now, to use our formulas correctly, we need the standard angle, which is measured all the way around from the positive x-axis. And in this case, that's 230 degrees. So we plug that in and look at what we get. The horizontal component is negative 32.14 pounds. That minus sign tells us it's pulling to the left. The vertical component is negative 38.30 pounds, pulling down. The mouth is just perfectly describing the picture for us. I love when that happens. Fantastic. We did the hard work. We've successfully broken down all three of those messy diagonal forces into simple, clean, horizontal, and vertical pieces. Now comes the really satisfying part, putting them all back together. So this table just lays it all out for us nice and neat. We've got a list of all the side-to-side forces in one column and a list of all the up and down forces in the other. All we have to do now is just simple addition. So what's the total horizontal pull and what's the total vertical pull? Okay, adding up that x column, we get a grand total of positive 42.24 pounds. So what does that mean? It means after all that tug of war, the net effect is a definite pull to the right.
And for the y column, the total comes out to negative 47.58 pounds. And again, that minus sign isn't scary. It just tells us the overall vertical pull is downwards. Simple as that. We are so close to the final answer now.
We've taken 3 chaotic forces, and we've boiled them down to just 2 things. One simple horizontal pull and one simple vertical pull. Now it's time to combine these two into this single final overall force, the big answer. And how are we going to do that? With an old friend you probably remember from geometry class, the Pythagorean theorem. See, our total x and our total y pulls form the 2 sides of a right-angled triangle. The final force we're looking for, the resultant, is just the hypotenuse. So we just square the sides, add them up, and take the square root. So we plug our numbers in, run the calculation, and boom, we get our final answer. The resultant force is 63.62 pounds. That's it. That single number represents the combined total effect of all 3 of those original pulls on the hook. So let's just step back for a second. What did we actually do here? We started with what looked like a really chaotic system, right? 3 different forces, 3 different angles. But by using this method of breaking things into components, we turned all that complexity into one clear, simple, understandable result. And you know, this way of thinking, it's not just for a physics problem on a hook. We took a complicated problem and we made it completely manageable just by breaking it down into its basic parts. It kind of makes you wonder, right? What other complex challenges out there, maybe in engineering or finance, or even just in our daily lives, could be solved just as elegantly if we could only find the right way to break them into smaller, simpler pieces?